we got a few experimental results over a normal hardware, let's say with a sound card which allowed for a pretty tight timing of the jack audio cycle. Linux kernel was 2629 scheduler, as I mentioned, the old AQuoSA scheduler. As a workload, we ran jack in parallel with a synthetic real-time application, RTApp, which is a common, simply a typical real-time model computing a given CPU power every given cycle. And we measure the performance with these two things running together. What can we say? Well, we have a number of configurations here. We have on the top here the performance measured in terms of the jack and driver timings used for jack on the top. On the bottom, there is the delay instead. So let's say the response time of our real-time application. The real-time application was having a period of 40 milliseconds. The jack application here was configured with a period of 1.3 milliseconds. So what we can see is that by using the normal Linux scheduler without any hacking, any tweaking, we are seeing that CFS, so the default scheduler for both, we are seeing that the jack application is actually behaving well, and the real-time, the RTApp application here is getting some artifacts, so it's getting some deadline miss. Here there is the deadline, the ideal deadline of my application, and getting some deadline miss, so there's been some misbehavior. Basically, the scheduler is preferring the jack application, is kind of boosting it because it's detecting it as more interactive. As you know, this is due to the heuristic internal to the default kernel scheduler for handling real-time workloads more interactively than batch workloads. If we run the two threads at the FIFO priority, but we use a bad configuration, for example, if we give to the RTApp more priority than the jack process, then what happens is that RTApp runs perfectly stable. It means it has a response time which is really practically a constant. Jack, of course, cannot. I mean, we have a lot of overruns and a lot of response times which are even higher than the picture. They are not showed, but as you can imagine. If we give the correct priority tuning, so the high priority should go according to the rate monotonic standard configuration to the application with the lower period, then we get actually RTApp behaving, jack behaving well, and RTApp behaving well. Well, everything is fine with priorities. If we use the AQuoSA scheduler, as I said, this is we basically have a good behavior of both cases. You can see both the jack is behaving. Both the jack application is behaving well with the note and the RTApp, they are both behaving well. However, as you can see, jack is having problems with the new clients joining the infrastructure. These segments are due to the 10 clients which are subsequently registering into the jack framework. So whenever a new client is coming here, I'm not really providing the perfectly needed budget boost whenever a new client was joining. However, that can be easily fixed by changing slightly the parameter and giving more budget boost. I wanted just to show you that this problem of budget identification may be actually tricky to solve. Finally, on the rightmost picture, I'm using the modified jack with the resource reservations. And with the soft resource reservations, and as you can see, I can get rid of all the spikes because even if the budget, even if the process is requiring slightly more than the budget, however, I'm able to run the process for more than the reserved budget. So I can exploit the unused capacity of the system. Also, we can see another picture on the bottom. Now I'm showing again jack, and in the bottom I'm showing simply 3 curves in the 2 rightmost plots, which are basically the allocated bandwidth. The blue one is the allocated bandwidth, and the green and red ones, which are basically overlapped, are the predicted budget, and the actually observed budget. So as you can see, there is the prediction that tracks very closely the what happens in the real system, and also as you can see on the new client, whenever a new client is joining the infrastructure, I'm boosting sometimes, as you can see here, I'm boosting a little bit too much. Then after a while, I'm boost temporarily. Then after a while, I adapt to the actual workload which I'm observing. So you can see here how wrong is my boost up or whatever else. I mean, there's just a configurable parameter, a tunable, that you can change. An alternative here for the new client joining problem is to actually maybe save into a file the observed workload over the past history of the system. So if you activated a filter another time, or maybe during deployment time when you install your filter into the system, you can benchmark your filter. You can benchmark quickly some of the basic operations, store that into a file, and retrieve the file later here and use that information to know what is the amount of boost up that you need when you load that filter and you activate it inside the infrastructure. I'm saying a filter because a filter is very easy to handle. It's basically a nearly constant time of execution. If it's going to be a MIDI synthesizer, then the problem is far more complex. Summarizing, we can say that we tackled the challenging case study for using our resource reservation schedulers in Linux, which is the Jack audio infrastructure, which really has low latency needs, so very serious timing constraints. The critical issue was really budget identification for this kind of application of our scheduler. However, we managed to have the performance of Jack alone to, let's say, to be kept as in the previous case without our machineries. The setup and deployment of a complex mix of real-time applications, however, may be simplified in this case because I don't need any priority tuning. I can analyze each application in isolation. I can know in isolation what is the computing requirement of my Jack audio infrastructure. This has nothing to say to. I don't need to know anything about what else is deployed on the system. In the other case, with priority tunings, as you know, whenever I decide what priority will I run my application, I need to know what other applications are in the system, and I need to hand-tune these priorities. How it was shown probably in the first day by Jeremy, in the talk by Jeremy, which unfortunately I couldn't attend. So that's the main advantage that we can get here. We can get each application developer to focus on its own application, embed code a way to understand what are the computing requirements of the application, declare them to the scheduler, and I'm done. I don't need anything else. However, the work is far from being finished, also as evident from some of my notes. We need a better handling of budget boost for new clients. We need the collaboration from some clients which have really very dynamic workloads which cannot be predicted. I'm talking about the MIDI synthesizer. That's one of the most challenging Jack clients for us. And we need to test this with a more recent scheduler, with a preemptive version of the deadline-based scheduler. And we need to experiment with the SMP and parallelization for high-performance Jack clients. Few related publications, and thanks for your attention. If you have any questions.